So, hello everybody, and now it's time to start session number 5 on statistical energy analysis and hybrid methods. This time we will talk about systems, and it's an important chapter because we talk about systems with single or multiple inputs and outputs. And the most important thing there is that we will deal with how to calculate the response of such systems to random excitation. And that's the typical case that we have when an SEA or statistical subsystem is exciting the boundary or a neighboring subsystem. Let's go to the details. So we might consider any car, building, airplane, or whatever under technical system as a dynamic system. And often such a system is excited by sources, which is given by the function f. It could be a force, it could be whatever. And this excitation is what we call the input of the system. In a very simple case, that means if we have just one response, often denoted by G, that's what we call the output of the system. And if it's just one single input and a single output, we call this a single input, single output system, obviously short SISO. When we have multiple inputs, say n input functions, and we have multiple here m output functions, then we are talking about a multiple input and multiple output system. Here the short form is MIMO or MIMO, however in what language you pronounce it. And every system is expressed or described by a functional expression h. So capital H that relates those inputs to the outputs. The good thing with such a description is that we just focusing on those degrees of freedom of our technical system that are important. So that means all the mounting points, junction, possible excitation points on the input side, and all the receiver points on the response side. For instance, the driver's ear, vibration at foot location, whatever. Here we definitely are considering linear systems. They are characterized by those two equations. So that means if we have the response of the sum of two functions, it's the sum of both responses. And the same is true if we're using linear factors for the function where we have the same impact. So a doubling of a force leads to a double response and not to another relationship. Let's come to one classical and good example. We come back to our famous damped harmonic oscillator. If you remember well, the excitation of a force, here our input, in terms of displacement, our output, is given by this fraction expression here. So here we consider the displacement and the force as complex amplitudes, and then we can define the function that denotes the system response in the frequency domain by exactly this fraction, because G, capital G as a responsive function domain representing the displacement, is just the function h multiplied by the force spectrum. And this is the given function, which is quite logical if we check the equation on top. So this is the transfer function in frequency domain, and obviously, because there are some complex terms here, it's a complex function. We can do the same or similar thing, let's say, in time domain. You know that to get this into time domain, we have to use an inverse Fourier transform, and a Fourier transform of a product or function corresponds in the other space in a convolution in time. And according to our Fourier transform formula collection. That means if we would like to express the response in time domain, meaning that we have our function over time, we have to use a convolution. and the response function is given by functions small or just function h. And the same, we can exchange the variables, and then the same convolution equation would look like this. We all know that there could be no response before there was an excitation. This is what we say, this is what we call a causal system, and that means that the response function must be 0 for all values of the time smaller than 0. So this leads to a new arrangement of the integration limits. This is from 0 to infinity, as shown here in this equation. So the biggest change is the lower frequency limit. So anyhow, all those forms are convolution integrals, and the response can then be written in this special notation. So the operator of convolution is denoted by this famous star symbol. Also very important, please don't mix the convolution with the correlation, because they look similar. If you keep in mind, convolution is always with a minus, the correlation comes with a plus, which is, has a different meaning. So there's no comparison of signal, it is just heading in the other direction. So that so far for the time domain. That means with this function h, we can express the response of a linear system in time domain. And to understand better what is this function h, what is a good physical interpretation of that, we use a trick. The trick is that we say, okay, we are interested now in the frequency response of our system given by this frequency transfer function to unit frequency excitation. So we have all over the frequency range always the real amplitude 1. And and this is what is the nature of this trick? The trick is that we can use the formula for the inverse Fourier transform of the unit spectrum. So we can write 1 in a special way, like this. Say that t index 0 is 0, and then we know that the inverse time domain, that this is the delta function, because the inverse function of the e function is, according to equation 38, a delta function. So, as we also know, this corresponds to a convolution in time domain. This is the small function h, and this is the thing that corresponds to the delta function. And then we got this expression for h. And this motivates the formulation, or let's say an expression that is used for our function h, because this is the response to a step, to a delta, to a very, let's say, impulse-like excitation. And this is the reason why we say that's the impulse response of the system, or the impulse response function. So let's get back to our famous harmonic oscillator in time domain. And we can just use the inverse Fourier transform of the frequency response that I've shown before, and then this should reveal the impulse response function. If we do so, that's here the expression, we get this result. So it's a damped oscillation with a sine function and a specific phase that is given by a factor at the beginning. So at the same time, this is also the solution of the following equation of motion. So that means the excitation here logically is the delta function at time, and this is the equation of motion for the harmonic oscillator in time domain. We can translate this into let's say a physical meaning. That means it is the same like using the following initial conditions. So no displacement at time 0, but a given speed which corresponds to 1 fraction 12 the mass of the oscillator. So a good physical figure is that you imagine that the oscillator is hit by a hammer, introducing a specific velocity in the beginning. This is again a good picture or a good figure for the impulse response. A hammer will definitely provide an impulse into our mass. So To conclude, with the definition of system response functions in time and frequency domain, we can calculate the response of every linear system. So now let's extend our single input and output system to a multiple input and multiple output configuration. And this is the moment when matrices and vectors come into the game, as very often shown before. So just imagine that you have a force, as it was shown in multiple mass system in the sections before, and you have a matrix of transfer function that providing all the displacement responses due to this force excitation. In the in the derivation that I've shown before, that means the multiple mass and spring system and the configuration of session 3, I guess, you see clearly that this transfer matrix corresponds to the inverse of the stiffness matrix, because it was on the other side in the equations before. Here, specifically equation 22. So again, we can do the same for the time domain. But anyhow, first of all, this matrix is a matrix Mn, because we have n inputs and m output functions, and this would give that's the dimension of this matrix. It doesn't have to be a square matrix or so, but it could be rectangular definitely. But then we can do the same in time domain, and then we have lots of specific impulse response function with the index Mn. And let's say we are interested in the output of the channel M, then it would be the convolution integral convoluting all the single force components using all the single impulse response. So, and giving more or less quite a complex formulation. The same could be done in the frequency domain for one frequency spectral output for channel M. We have to do the same, but it looks much easier because there's no convolution integral involved. I personally really like to put this in matrix form because I can better think in matrices. And this would look like this. So you have a full matrix with all the coefficients of the transfer function. You have the force vector here, and you have the response vector on the left-hand side. Good. However, those equations are useful, and they are definitely needed, but they can only be used if you have a fully correlated input. So what happens if we have a set of n excitation signals that are random with a given cross-spectral density? So that means we would have to formulate the relationship among each possible signal combination. So that means, and this is a little bit confusing maybe, but just imagine that now M is not the index of the output, it's just another version of another version for N. It means we have to correlate any input force to the other input forces or excitation. And this is, as mentioned in the session before, the easiest way to do so is to do the expected value average over many measured spectra. So the trick is that the FF denotes that we are just talking about the input channel. We are not relating input and output, we're just dealing with the input. And MN is denoting that we're talking about the different channels of the input. That means our famous cross-spectral density matrix would look like this, again in matrix form. We will have all the autocorrelation here on the diagonal. We have the off-diagonal terms given by this, giving each correlation between channel 1 here, for example, and channel N. And due to the symmetry of our cross-spectral density, we know that this is a Hermitian matrix. So if we exchange the indices, we get the conjugate complex of this function. Good. So, but anyhow, that means in short, for describing a random input, we need this matrix. Important to know, if you have, let's say, 100 input function, we are ending up with the 100 times 100 square input matrix. This is what we need. We would not get another option to deal with a correlated input. For the convention, it's quite helpful to do this in vector, to describe this cross-spectral matrices in vector form. And because of the vector convention, we say that we multiply the row times the column. We can write this matrix in a much easier form. So we take column vector as first argument and the row vector as second argument. And let's say for every matrix coefficient, we have to take the row, which is this here, times the column. And that gives a full matrix. And if we write this in a small form, it would look like this. So F complex conjugated multiplied by the transpose of the input force. Sometimes, especially in literature on hybrid theory, the complex conjugate of this is used, and this would look like this. We just get rid of this conjugate term here, and the only difference is that we have a non-conjugated version here and the Hewittian form for the second force factor. Let's come to some example to bring some insight. What are typical related versions of random excitation? A classical and often used example for totally uncorrelated excitation in the rain on the roof. When you have a plate, the drop that is hitting the plate here has not any correlation between the drop that's hitting here. So because it's a single drop, maybe they experience the same cloud, but I think you will hardly find the correlation relationship between both excitation from the drops. That means that the matrix describing this excitation would be 0 for all off-diagonal terms, but just the diagonal would give the autospectra of each single drop excitation. Let's come to an example for fully correlated excitation. Just imagine that you have a combustion engine which has a rigid body motion and has lots of vibration, whatever. But one thing is clear, all this vibration comes from this stiff block, and whatever force is exciting any mountains of those pushes, it will definitely be correlated, and in many cases, and especially for the most harmonics, it will be fully correlated. So that means we will have a fully set matrix, but again, we should not forget, if we have a fully correlated solution, we can stay with the solution as was given before. However, if we have a fully uncorrelated solution, we can also use this formula, and then we just squaring up the responses and get the autospectra of the responses. So both extreme cases of random input, fully and uncorrelated and correlated, we can still use the single excitation case. For all other cases in between, where we have partial correlation or cross-spectra relationships, no way. We have to use the full matrix. So, when we know the excitation and the random character of the excitation, how can we get the cross-spectral matrix of the response? Because the response must also be a random output. If the input is random, the same must be true for the output. So we write the output in this form, as was shown before. That's why we're using this famous vector form. And now we write each component of this product in the matrix form. So this is the complex response with the response function and the force. And if we transpose this changes the order. So we have the transpose force vector here and the H matrix on the right hand side, and we just put this into this equation. So here we just have also denoted this by showing the details, but however, if we enter this directly here, we will get this form. So we have the H matrices here on the outside, and we have here in the middle a term that we know. That is our cross-spectral density function in that as we have also used to describe the excitation. The H matrix has no random change, so that means we can remove this from the expected value operator, and if we do so, the equation would look like this. And now again we have our expected value formulation for the cross-spectral density of the excitation, and this would exactly look like this. So we have a triple matrix multiplication to get the multi-input input-output system response to a random load. Again, if we use the other version of it, sometimes we can use the complex conjugate version of this, then we have to write this equation here. I'm once again showing you this because, again, in hybrid literature, very often this form is used and not this one. This is just to help you to get into the details of this. One remark is very important here. You must imagine that the single excitation, that's an H matrix, exciting a force, and then you can calculate the response. That's an easy operation. When we have to deal with random excitation, our simple matrix equation is now blown up to a triple matrix multiplication. So this here is rarely solved directly. There are multiple tricks to do so with singular value decomposition, finding out the major components, triangularization, whatever. You will find this in some papers that I tried out to describe this, but please keep in mind, this is an operation that is, even with modern computers, rarely done. So for instance, if you would like to calculate the response of a fuselage skin to random excitation like turbulent boundary layer, and you easily have a fuselage with, let's say, 1 million elements, that means your excitation matrix describing these 1 million element excitation would be a matrix of 1 million times 1 million. So you are really, even in terms of memory, this is a very high computational expense. Good. So far for this, and now let's come to some conclusions. They are including also the conclusions on our network of discrete strings and dampers. So complex system can be modeled by a network of discrete strings, dampers, and masses. Fully uncorrelated excitation can be a step-by-step calculation can be applied for every input. So the linear case can be used, and that means that the situation is quite as simple as it is the case for the fully correlated case. However, if we have partly and random excitation, as we have a lot in our statistical energy analysis case, we need an expensive triple matrix multiplication to deal with such an excitation. So anyhow, so the problem is that we will see that later on that the concept of a diffuse or reverberant field, this is the description of our random subsystems, and exactly this random wave field is given by cross-spectral density. But however, we have now the mathematical toolbox, but you can be sure you will not use a direct calculation of it. That's computationally too expensive. Okay. So then, thank you again for your attention. That's it with linear systems, signal theory, and random processes. And the next sessions will be about waves. Structural waves, waves in fluids, about sources, and so on. And we start with fluids, because fluids are the simple case. Just in 1 degree of freedom, in most cases the pressure. And we will learn a lot about sources, and the sources are important because those are the guys that tell us how energy is introduced or power is introduced into our system. And also, as we have an energy analysis method to explain, we will also learn how energy is stored and transported in waves in general, and in the first step for fluids. So hopefully see you again for session 6 on waves and fluids, and I wish you a good afternoon, morning, whatsoever. See you, bye bye.